Yep.
Great.
Can you go to the slides?
Sure.
I have the notes.
Okay. Let's see.
You can share it on your computer.
Oh, okay. My computer. I think the computer is kind of strange here.
Yes.
Do you want to see your slides?
Okay, I'll just use my computer.
Okay. So are we waiting for students again? Oh, we can
I
start.
think we can start, but the slides are not visible.
Yeah. Hello, guys. Welcome to Recitation 2. This will be about ablation, hyperparameter tuning, and normalization. So this is to help you actually for the homework on part 2, to help you achieve, let's say, high accuracy. All right. So it will be done by, sorry for the presentation. So by me, Romric, Alex, who is online, and Puru here. So we start by data manipulation. Sorry for this. So in data manipulation, we talk about data augmentation and also data normalization, right? How can you process your data before actually feeding it to a model? To kind of improve actually your model accuracy somehow. So the first one is data augmentation, and sometimes actually the kind of data you are feeding to your model, right, cannot be, let's say, sufficient to generalize. You like your model to see your data in whatever the form, right, many forms. So in this picture, for example, you have a picture of a cat, but if you are sending this cat picture to your model, just this kind of picture which are clear, completely clear, right? So the model can understand, clear picture somehow. But when you will come with blur picture, image that are completely red or blue, so it may struggle a little bit. So that's why you apply kind of data augmentation to that. So data augmentation is kind of just applying some uh, augmentation techniques, right, like rotation, scaling, changing perspective, and whatever to your data. So you have your original data, but you kind of copy them, and while copying them, you add these augmentations, right, and then it's kind of a way to double your data set or triple it somehow based on the augmentation you have been applying to. And then your model will be able to see your data in many forms, right? That will be better for generalization. For in this example, by here, we can show the model this card. Can you see this? So this card here we flip it. Here you see, and in different ways somehow, right? And also here we apply some kind of blurring it, yeah, right. So I don't know if you have any question about the data augmentation. And it's not just done for images, it can be done for the MFCC stuff. But I think in your case, your MFCC has been already proceed, right, a lot for you. But by example, for homework 2, part 2, where you will be doing image classification, this kind of stuff, it will be really important for you to apply augmentations. And you can see the different augmentation that you can do to your data set on PyTorch website. If you go there, data augmentation PyTorch, you will see there is a list, and you can just apply different augmentation for that. Good. Any question? Yeah.
So for MFCC data, should we bother like flipping the matrices?
Sorry, can you speak up? Can you hear?
For like MFCC speech data, should we bother like flipping the matrix?
Spec augment.
Good. Yeah, I just reply to it. I can hear it.
There's spec augment.
Okay. So if I,
High frequency masking.
yeah. So if I understand your question, you are asking about the padding for the MFCCs?
No, what augmentation you can apply for it?
What augmentation we can apply for this?
Yeah.
Okay, I think quite a lot. I mean, those augmentation you can have access to in signal processing. And what are they right now?
So for the MFCC data, there's this thing called spec augment that you can apply. So like you randomly zero out channels in your time axis and frequency axis. I think we'll be going over that later. So.
Any other question? No. Okay. Okay. So the other technique is data normalization. So when your data comes somehow, let's say the pixel images, it's kind of the density of the color, and they go from 0 to 255 somehow. And as this number are kind of large, when you are feeding it to your model and it's going through all these functions, activation, and everything, so the weight actually of the numbers through your model can start becoming really big, right? And this may lead to some issue. So the model can struggle with big numbers, and while doing the back propagation, you can have, I don't know, gradient which are really big because actually your numbers are really big. So applying some kind of normalization, right, before scale, putting your values between a range that's kind of small, or most of the time we do between 0 and 1, or -1 and 1, can really help your model somehow, right? So you have the Z-score normalization, mass scaling, standard scaling, different kind of normalization. So, or what they do, as you can see here, they kind of center your data from this big space they were into a kind of small range right where they are, and then this will really, let's say, speed up first the computation and help your model in the computation. And here a little bit, description about each of them. So the self-farming normalization is efficient normalization technique for robust speech recognition. Right? So in this homework, exactly, you need to do some research about those normalization that will be better for your case here. And for other homework also, for image, by example, which kind of normalization, and yeah. So it will really depend on the case, right? But normalization technique will help you, to put everything kind of in the same range, which can help speed up, your training. Now for your ablation, how do I think about model architecture for homework one part two, right? As you might know already, one of your two biggest tasks is to find the right model architecture. So you have to train it and also find the right parameters, do the hyperparameter tuning, and actually to have a high cutoff, right? So you have to experiment different architectures. So there is no an architecture that's there, and we know that if you take this, we have the high accuracy. You need to test different architecture to know, actually, to see, okay, which one is working best, which one is not good for my case. And also something I can add is that you can also read actually some papers, right? Here, as you are dealing with speech recognition, we can look at paper related to speech recognition or classification, and see the neural network that those guys implement, which kind of architecture they use, right? As they have already gone through a lot of research, and then they come to, let's say, nice architecture, right? So you won't be required to go through all this hard process they have been doing. But yeah, in this homework, you can still do that, right, to find what's best for you, and also what's best in terms of hyperparameters. So we talk about the hyperparameter tuning also after this. And you have different model architecture you can try. So this one is the diamond, right? So when you are implementing your layers or your model architecture, you start with, let's say, I don't know, layers with uh, 5 to 12 neurons, and then after that, you increase the number of neurons, you increase, and after you reduce, you reduce. So it's make like a diamond architecture somehow, right? So you can try that, and so that you have the pyramid. So the pyramid, sorry, the pyramid or inverse pyramid. The pyramid, you just start with few neurons, and then you increase, and the inverse one is you start with a large number of neurons, and then you decrease. So yeah, I mean, I think the images are kind of self-explanatory. This is the cylinder one. Cylinder one, you kind of keep the same number of neurons for all the architecture. And please, while trying all those architecture, be sure that you don't go more than the 20 million parameter that are required for your homework, right? Because if you go more than that, I think we have some issue while grading your assignment. So this one is a hourglass, so it's kind of a pyramid and an inverse pyramid together. All right. So yeah, that's a little bit the summary of what I've been going through now. You have also to take some activation function. We talk about it right now. Batch normalization. I think you have seen it already in the lecture. Or not yet. Dropout. I mean, all those things we talk about them right. Thank you very much. I will go for the ablation. So that's Alex, right? Alex, are you there?
Yeah, I'm here. Can you hear me?
Yeah. So you want to share a screen?
Yes.
Sure.
Okay.
Great. Can you do slideshow? Yeah. How do I hide
Okay.
this?
Is it good?
I think so. Yeah, just go.
Okay. So next we'll be covering schedulers and learning rate. So what are schedulers for? So schedulers, they control your learning rate over the training process, right? So the learning rate is an important parameter because it's one of the factors that go into how big of a step your optimizer takes. And this affects not only how fast or how slow you train, but also what kind of minima you converge to. So the learning rate is important because, again, as we say, that it's important to determine the kind of step that your descent algorithm takes. So if it's too low, it means that you're taking too many steps and you're not getting there fast enough. You'll get stuck in the early local minima, and you'll also take too long to train. If it's just right, then it's a good trade-off between, fast convergence and also not missing the minima. If it's too high, then you're just bouncing around the loss landscape and not descending to a minima. And these are very clean loss landscapes and really not practical. So I was just trying to find something that can probably kind of approximate what we should be thinking about. And like, this is a decent visualization tool just in 3D space, but you should imagine the loss landscape in very high dimensional space. So you have so many local minima and a global minima. And chances are that the optimizer is taking steps down. It will probably end up in a local minima, but you want it to be a good local minima that's not too far from the global. Okay, let me go back to the slides. So yeah, let's cover a few schedulers that are available in PyTorch. So StepLR, it takes in two parameters. One is the step size and two is a gamma, which is a multiplicating factor. So after this number of steps, it will multiply the learning rate by gamma and therefore reduce it. So you can tell what this will look like over time, because let's say if it's 0.5, means that after 4 steps, it goes down to a half, then goes down to a half and a half. And it's kind of exponential, but in steps. cosine annealing, it reduces the line rate by a cosine function. So there's annealing and there's annealing with warm restarts. So in this case, the line rate is descending along a cosine and then it shoots back up. Why do you want your line rate to not just go down but also go back up? Because raising the line rate after some point allows you to get out of your current minima and then explore the landscape. So you'll probably find either the same minima or better ones. That's the goal of such a schedule. It takes in 2 parameters in this case. So actually the warm-up restart has more parameters, but annealing takes in 2, which is the max length, max number of steps, and this is the minimum value of the learning rate that you will descend to. So you don't want to just get arbitrarily small. You want to define it to something that's predefined. So other learning rates also monitor certain metrics. So reduce LR on plateau, it monitors some metric that you pass to. So what we recommend is the validation metric. So either validation loss or validation accuracy. So what you do is at the end of your validation cycle, you feed in that metric. So what it does, it monitors whether the metric is improving. If it's a loss, it checks whether it's going down. You'll set a parameter called patience, which, as it sounds, it's just if you don't see the parameter improving, wait for X number of steps before reducing the learning rate, right? If it improves and then, let's say in this case, it doesn't improve again, so it will need to reduce after X number of steps. So this is a good one because it monitors a specific metric. It's not just arbitrarily reducing the learning rate. So it keeps it as high as possible until you stagnate and then lowers it so that you can improve. Yeah, so any questions on schedulers? There's also a couple more, but this is just to get you started and to get looking into scheduler.
Sorry, can you explain, do you mind going back a slide?
Yep.
Say improvement, isn't reducing the learning rate, like, you're not, I don't see how reducing the learning rate, I guess, would improve it more. Like you're bouncing around and then you decrease so you can sort of descend further, or?
Yes. So it assumes that stagnation means that you're bouncing around in this case. So you want it to get lower so that you descend instead of staying at the same place.
Okay, thank you.
Yep. Okay, cool.
Hello, a question from the Zoom.
Yep.
I have seen the manuscript, the document of PyTorch, and I have seen that they have used two scheduler. They use them together. Is that normal in our applications? And can you explain that?
Sorry, they use what? 2 schedulers?
They use two schedulers. Usually, the first one is like the step, and the second one is like the other, like the cosine or other scheduler. I've seen they use two scheduler on the PyTorch document, but I don't know if that is normal in our application.
Actually, I haven't tried that before, and I don't know if many of the TAs did experience with this over the break, but sometimes what I see is people adding, for example, like warm up, which is a common thing. For example, like people generally say like you need to warm up transformers. So you start, instead of, if this is your initial learning rate, you kind of start from a lower value, then bring it up, and then start from your initial one after, let's say, like 5 epochs. But as far as combining, I think it's interesting, but it also introduces more hyperparameters to experiment with. So it could work, it could not work. So, but I also don't know enough about that. That's
Okay, thank you.
yeah. Okay.
Sorry, Alec, may I add something?
Yep.
So about this one, actually, yeah, you can use different scheduler, and the way you can do that is maybe you can be let's say monitoring your accuracy. I don't know, your validation accuracy if you want, right? And using the first scheduler, maybe the step learning rate scheduler, and if you are using it for, let's say, a long time and you're seeing that you are no more improving, right, you can kind of switch to the cosine. Can you hear me? Yeah, you can kind of switch to the cosine. So it just depends on how you design your code, right? But yeah, for this homework, it's not kind of mandatory to use 2 or 3 at the same time. You can just try with each of them. But the thing is, when you are trying with the step learning rate scheduler, you have at a certain time to stop your code, right? And then try another one and see how this one is performing. But you can try to do that automatically and see, if you're not improving, how you can just switch to another scheduler somehow. All right.
Okay, cool. So let's go to normalization methods. So there's a couple of them. These normalizations are different from the ones that were talked about in the first portion. So those are more they're applied on the data itself to try and improve the ability of the model to extract features from the data. In this case, we're applying normalizations mostly for improving training. So not just convergence, but also the speed of training. And there's a bunch of them, and here's a figure that should kind of illustrate that. So you have, we have batch norm, a few of the popular ones are this four, right? Batch norm, layer norm, instance norm, and group norm. So batch norm, you're applying it across a mini batch, right? So you compute statistics for mini batch and then normalize for the mini batch. Layer norm is different. You're doing it across the channel dimension, right? Which, again, the motivation is still the same. Batch norm, the goal is to, we'll probably cover this in lecture 7. It's to reduce internal covariate shift, which affects the speed of training, right? The goal of layer norm is the same, but it just applies the normalization across the channels instead of across a mini batch. Instance norm is for a single instance. You probably won't see this too often, and actually I haven't seen it too often. So yeah, let's just not spend too much time there. But group norm is another interesting one. So people have found that sometimes computing statistics across the entire set of channels is not, how to say, it's way too dense. It's not efficient, not just efficient, but it's also not the most meaningful way to get the statistics. So sometimes you take groups of neighboring channels. So for example, like if it's a very long sequence, instead of taking the whole thing, just take groups of them. So there's a parameter for group norm called the number of groups, which divides the channels into num groups, right? So you can probably see that layer norm is a special case of group norm, where the group is 1. So it basically divides it into one group, which is the exact same thing that layer norm is. Group norm is a bit newer than, so batch norm is the oldest, layer norm is newer than group norm is, I believe, the newest of this. It's shown to provide better results, but it introduces another hyperparameter, which is not always a good thing. So batch norm allows for higher training rates and faster convergence, which are the two main things, right? So internal covariate shift will be covered in, I believe, lecture 7 or lecture 8, and you'll probably be able to get a better sense of why you'd want to reduce the covariate shift in your data, because it's like having different distributions at different points, and you want to bring them to like a common mean and standard deviation. So that allows for faster training and better convergence. But the problem with batch norm is, since you're computing statistics and normalizing across the batch, it's highly dependent on the batch size. And people have found that the performance is really poor with small mini batch sizes. So you need to keep your mini batch sizes quite large if you want to use batch norm, which is actually why people came up with things like layer norm, which is what is used, for example, in the transform architecture. They use layer norm and not batch norm. So if you have high dimensional inputs, you can't fit big batches on your data, right? Also, if you're using like distributed training, you can't do batch size across all the nodes, across all the GPUs. So the batch statistics and normalization will be per device. So in that case, the effective batch size is the per device batch size, which again, it's too small, the performance will be degraded. So that's why you need to be careful with batch norm and keep the mini batch sizes large. Also, the running mean and variance, which are the batch norm statistics, may not be the best for sequential models and sequential problems, like when you're dealing with RNNs and transformers and in general sequence to sequence or sequence problem. So yeah, batch norm is not perfect, but actually in the group norm paper, they found that it tends to converge to the best values for most problems, at least most problems that they experimented with. So yeah, that's the end of normalization. Any questions on that?
Minimize the Zoom thing so we can see the slides.
Sure. Could you, you minimize the screen on this side? No.
Hi, can we find the slide on Canvas? We'll upload the slide to the Canvas.
Yeah, the slide will be on Piazza. Yeah.
Oh, okay. Thank you.
Okay, cool. We can go to the next thing.
You want it right?
That's fine. Or otherwise, you can make it full screen.
Yeah, could you just make it full screen? Collapse the speaker view. Collapse the speaker.
Okay. Romerick, is everything good on the other side?
Just 1 second.
Okay.
And then,
Yeah, that's fine.
sure.
Thanks.
All good now, Alex.
Okay, cool. So what are hyperparameters? This let's say external settings, external parameters that control the training process. So the parameters in this case are the model weights and biases. But hyperparameters are things that a researcher, scientist, or engineer will set. And these are things that are either specific to the task or they're supposed to govern how the training goes, right? So that's the difference between parameter and hyperparameter. Why do we need to tune them? So one is we want good performance on our downstream task. In this case, we want better accuracy. We also want faster convergence because we don't have infinite time, and we also don't have infinite compute. And we also want to work within our resource constraints. So, train with, as little time as you need and as little resources as you need. And you also need to get to the high cutoffs to get the full marks for your P2s. So that's why you need to tune hyperparameters. And there's a bunch of hyperparameters in this case. There's the size of the mini batch size. There's the mini batch size. There's learning rate and schedulers. There's dropout. There's the context. In this case, because it's a sequence input. It's phoneme. It's MFCC. Sorry. There's also this architecture-specific hyperparameters. There's the optimizer and also weight initializations. For example, like just to preface a bit, for homework 2, we'll have CNNs, and you have different building blocks, right? So you have conv layers instead of linear layers, and they introduce a bunch of other hyperparameters. Let's talk about context. But first, let's go over the tasks. I think we kind of noticed that there were quite a number of questions that kind of showed that the task was probably not that well understood. But so what you're dealing with in the original data set is it's speech, right? So in this case, let me just play this. Yeah, I don't know if you could hear that, but it's basically an utterance of someone saying hello, right? And the phonemes that correspond to the speech is, these 4 phonemes, which are the spoken language units, the sounds that are in the speech. And so for audio data, you basically represent it most commonly as a waveform. So it's amplitude by time. And in this case, the time you have samples, which, for example, could be like 16,000. It's a very, very high number. So 16,000 samples per second. Then to be able to get to MFCCs, you first compute a MEL spectrogram, which you probably don't need to know the entire process, but so you basically take frames from the audio. A frame is like a 20 millisecond to 40 millisecond segment within which it's assumed that the signal is mostly stationary. And you apply a fast Fourier transform to each of the frames. And what you end up with is a spectrogram. And in this case, you also convert it to the MEL scale, which is it's a scale that's almost logarithmic, but it kind of represents how humans perceive audio, because we tend to perceive a lot more on the lower end of the spectrum than on the higher end. Then from a MEL spectrogram, you apply the log and the discrete cosine transform. In this case, you've also normalized the MFCCs. So this is the kind of data that you're feeding into your model. So hopefully that's a bit clearer. But a good question here is how we add context. So you probably worked on, I assume that you all worked on the early submission for P2. And in your initialization method for the dataset class, you are doing some operations to be able to prepare the data for adding context. So first of all, context, in this case, we assume it's bidirectional context. You can think of it as left and right context, which is the frames before and after the frame of interest or the indexed frame. So here, let's assume an MFCC of shape time by frequency components. So let's say T by F. So you have T rows, in this case, 5 rows and 3 columns or 3 features. In your get item method, so there was one thing being passed there, which is the index. So let's say in this case, we want the frame at index 2, and we want to add bidirectional context of 1. Right? So this is the frame that we care about, but we also want to get this too. So if you think about how this is going to be, this is probably one of the cleanest ways to do it, and to be able to guarantee that you will always have some context. So what you do, the first thing is you pad it at the end with rows of zeros. The number of rows of zeros that you pad it with is equals to the context, right? So in this case, we had 1 row of 0 because we want a context of 1 at the top and at the bottom. So you can think of this as like you're extending it along the time scale, right? So you pad it at the ends, and in your get item method, you set a start index, which is the one that we want. In this case, 2, right? The stop index will be the start index 2 plus 2 times the context and plus 1, because we also want the 1 in the middle, right? So what you do here, you take a slice of this extended matrix. So you start from the start index, which is 2. So 0, 1, 2. So the first one that we take is 4, 5, 6. We add it here. Then we take the next one. And since it's Python style notation, right? So 2 is inclusive, 5 is not inclusive. So we take 4, we take this row, and this row. And this is how we get bidirectional context of 1 for our target frame. The reason why we do it like this is that you can also take care of the cases where, for example, like we want the frame at the end, right? In this case, if you pad it with zeros, you can also be able to take the context for the frame at the end. It's just that on the other side, it will be zeros, right? In this side, it will be actual values. In this side, it will be zeros. But with this, you can guarantee that for whatever context value you need, you'll always have the exact shape that you expect. And so here's how you get bidirectional context. And context is a hyperparameter in this problem, right? Because we're dealing with an input which is itself a sequence. The MFCCs are frequency coefficients across time, right? So for you should probably picture that. Let's argue both ways, right? Why should we want longer context? A frame, as I mentioned, is something quite short, like 20 to 40 milliseconds. Most human sounds, at least at normal human rate of speaking, you probably won't say a full sound within 20 milliseconds. So you want to capture a full sound. So you need longer context in this case to get the MFCCs that correspond to a full sound at the very least. Two is, this is, just a common saying from a linguist called Fritz. So he said you shall know a word by the company that it keeps. Here we've just said you shall know a phoneme by the company that it keeps. This basically means that it's easier to predict what a phoneme is if you know what the neighbors are. So like if you hear the phoneme before and the phoneme after, you can probably get what the one in the middle is, because over time you have a sense of how these things kind of follow each other. So this is what we also want the model to learn. But you can't just have arbitrarily long context, because the MLPs, so the model we're using at MLP is based on linear layers. They're not designed to work with sequence input. In fact, the model probably doesn't even know that this and this are, like frame 1 and frame 2 are following each other in time, because we don't have recurrence and we don't have, for example, the case of a transformer like positional link. So MLPs are not suited for this kind of task. So if you have context that's too long, the performance will definitely degrade. There's also another reason why context that's too long will not be useful, and it's from here. Can someone please tell me why context that's too long will not be useful based on this process of extracting context? Anyone? I'll give you a hint. It's the way we pad it. Anyone? Okay. Then I guess I can say it. So if you pad it if you have context that's way too long, you'll exceed the size of your MFCC. So you'll end up with a bunch of zero valued rows, which are not important, right? So if you get too long, you just add a bunch of zeros, and that's not meaningful context. So yeah, context so there's like there's an optimal point. So too short is not good, too long is not good. So please experiment to find the optimal values. So yeah, any questions on context? Okay. I guess we can jump to optimizers. So we talked briefly about the loss landscape and how the learning rate determines how one descends this loss landscape. An optimizer is an algorithm that's now given ingredients and step and the learning rate, it will determine how big of a step to take. So an optimizer is just a descent algorithm. And we have a number of them. The simplest is stochastic gradient descent. We have Adam, which is probably one of the most common, and Adam W and a bunch of others. So again, just think of this as the descent algorithm, right? So SGD was one of the first ones and was heavily used. But as you'll see in the lecture on optimizers, SGD has some shortcomings, right? So it's not keeping track of which way it's descending, right? So for example, like if, like if it's been going down in one way and it's trying to go down in one way, but it's not improving, it doesn't have a bigger picture of like the whole landscape, because it lacks something that will be called momentum, which tells it, this is like running statistics over time. You've been going this way and you've been descending. So, you can keep going this way. So optimizers like Adam, they have momentum built in. So they compute moments, and the optimizer in this case has a better sense of where it's been and which way is trending downwards overall. So optimizers like Adam tend to be a bit more efficient. They tend to use fewer steps to get to a specific minima. a specific point. And another thing that's important here to consider is overfitting. This is probably not the biggest issue for homework 1, P2, but it will be a big thing in homework 2, P2. So overfitting is when the training metrics are decoupled from the generalization metrics. So in this case, you have a validation data set, right? So you're computing the accuracy, for example, for the validation data set, and it stopped improving. But the training's accuracy is continuously improving, which means that the training at that point is decoupled and your model is no longer able to generalize. That's assuming that your validation data set is also a good representation of the actual distribution that you're trying to learn. So there's a couple of techniques that minimize overfitting, and broadly, all these things are called regularization. A common one is dropout, which you've probably seen in the bonus homework. So dropouts, it drops out a given number of neurons at a given instance. So dropout takes in a parameter p, which is the probability that neurons will be zeroed out. So like, let's say if after this layer, I add dropout with a probability of 0.5, means that the neurons from this layer will be zeroed with a probability of 0.5. So in this case, you're basically turning off, preventing it from the activations from going to the next stage. So effectively zeroing in the outputs. What that forces your model to do is, given the only neurons that are not zeroed out, to get the predictions correctly. And at each step of training, it's random, right? So it's not just applying dropout to the same neurons. It's applying dropout to different neurons at different steps. And what you end up with at the end, at least from the original paper, it showed that what you end up with is an ensemble model. So at one step, it's learned to use this neuron in this layer. At another step, it's learned to use this too. And so in inference time, you're not zeroing out anything. And so you're keeping all the neurons. And so it's what you have at the end is effectively an ensemble. So yeah, dropout is pretty important. I think it helps to, especially when you're playing around with your layer width, you can keep your width higher. But if you're using dropout, you effectively have a narrower width. So it kind of allows you to experiment with the width without actually changing the width. And some other small changes that you could make are like weight initialization. So people have found that instead of just initializing your weights and biases with zeros, you can apply certain methods to initialize them. So this won't make too big of a change in your training because, again, it's just at the very start of training, right? But some have been found to allow you to converge faster and sometimes help with problems of vanishing or exploding gradients. And some other techniques I think that are probably important. Early stopping, which as it sounds like is, when you see your validation score, in this case, accuracy, it starts to decrease, meaning that your model is probably overfitting. So just stop the training early. Don't continue training when you're not improving generalization on unseen data. So that's early stopping. It's exactly like it sounds like. Gradient clipping, so you set a threshold for the magnitude values of gradients. And so beyond a certain point, you clip them. You basically prevent it from going higher than a certain value, which helps avoiding exploding gradients. So this is the problem that you'll see later in the course, probably around, I believe, CNNs. But yeah, so it's something that helps prevent your gradients from getting too large, which can cause a lot of issues, even just in representing them numerically, because floating point numbers can only get so big, right? You'll have numerical overflow and other issues if they get too high. So yeah, that's it for regularization. Any questions on that?
Okay, Alex, we share now.
Okay, cool.
It's disappeared. There you go. All right. Hello, everyone. Can you guys hear me? All right. So I'll briefly be going over some general tips for your homework part twos and things that will be more useful for this part two. So can I get a quick show of hands? Who's using mixed precision training right now? Just one, two. All right, well, I'm going to try to make a case for why you should be using it. And I hope for your sakes that I do a good job. So what is the general idea behind mixed precision training? So you're on a high level, you're mixing between two data types. So between 16-bit floating point precision and 32-bit floating point precision. And the idea is that for certain operations, you can get away with using 16-bit floating point without too much loss in precision. And the main reason for doing this would be the big boost in training that you would get. Anecdotally speaking, from my experience, when I first started the assignment, my training was like 35 minutes in Epoch. And when I implemented automatic mixed precision, it was down to 15. Hopefully you guys see that kind of speed up on your end. So you don't have to really know how this is implemented by PyTorch. PyTorch gives you the tool to implement this on a very high level. You have PyTorch offers autocast, which will automatically detect which operations are suitable for switching back and forth between 16-bit and 32-bit. And then there's also this thing called grad scaler, which will scale back your gradients to update your parameters appropriately. So you would do this. It's pretty easy to do with just a few lines. The link here has some examples on how you would implement this for your typical use case for homework 1 part 2. But it also has examples on, let's say if you're trying to do gradient clipping, you would handle that a little bit differently. Or if you were trying to do like some sort of constraint optimization, like maybe adding a L2 penalty to your loss, you would handle that differently too. You don't have to worry about that too much for this assignment. Just focus on getting this set up for your part 2. But also, here's a caveat. It only works on certain GPUs, including the T4, B100, A100. Does not work with the P100. So definitely give this a shot. All right. All right, so here's some general tips to keep in mind for your homework part 2s. So like the search space is huge, right? You have so many things to try. Each epoch takes at best 15 minutes, and you'll probably be running 50 to 100 epochs, and that's like a generous estimate. So be smart about how you divide your task, right? So modularize your experiments. Try to divide your experiments into parallelizable tasks so that so one way you could go about doing this is to first find a baseline, right? Find a model that is performing, like amongst your study group, find a model that is performing reasonably well, and then experiment on that model so you can have insights that are like meaningfully applicable, right? So something we highly recommend you guys do is creating like an experiment matrix, right? So you have the rows represent different things you could try, the different ablations you can run, like your model depth, your model width, your different augmentation strategy, or your different regularization strategy. And the columns would represent the component you're actually ablating on. And as time goes by, you could start with like a pretty broad matrix, like, oh, did I use dropout? Yes or no. Did I use any regularization? Yes or no. And then as time goes by, as you start gleaning more and more insights, you could start increasing the granularity of your matrix, right? So there are a lot of things to, like I said, there's a lot of things to try. So something you might do at the beginning is just try some. So a very important thing to remember is that some of you might be new to deep learning. I was, and you'll spend a lot of time forming high-level intuitions about how things generally work, right? Like if my model's overfitting, what is the first thing I should try? If my model's underfitting, what do I do, right? If I'm getting nans in my loss, how do I even go about fixing that, right? So you will use this assignment to figure those things out, and you'll get better as time goes along, right? So look on, read papers, read different blog posts, try different esoteric techniques, but try it on a small subset to see you have it working first before you try scaling up. But some things to keep in mind regarding this is that your subset size must be reasonable, maybe 10 to 30%. And also to get meaningful conclusions, try making sure your subset is actually representative of your actual data set. So like try getting an even distribution of classes in your subset. But yeah, we can't stress this enough. You have study groups, and try to split tasks evenly and divide and conquer. Or don't be like me for homework part 1, where I just try to do it all by myself and failed. All right.
When will the cutoffs be released?
I think today. Was it today?
Yeah, we will release it by end of day.
Okay, Piazza? Or-
Yeah, Piazza. Yeah, Piazza. All right, so also there's a wide range of values to try for like different parameters, right? You have dropout, you have something we didn't go over is data augmentation, specifically for this homework. I would really advise you to look at spec augment. So basically, let me just, I think it's important. You get good gains from this. So this is your MFCC. You treat it as an image and you zero out portions. And yeah, just try it out. So you can zero things out on the time axis and on the feature axis. But as is with everything deep learning, there's a point of diminishing returns. So test different intensities of masking with your group. Definitely recommend. All right, let's get back. So yeah, you will be getting your cutoff today. Let's see. Gone over this. Make sure you talk to your study groups. All right, so here's how we'll go briefly over using 1DB. Has anyone started using 1DB yet? All right. So for this assignment, we won't really, well, we recommend you do it, but for future assignments, we will be asking you to submit your 1DB logs as a sort of proof that you've actually done the ablation. So it's recommended you get started on logging your metrics soon. But more generally, it's just a good thing to do. Like parsing through your TQDM logs is probably not as intuitive as looking at a curve like this. So what you could do is, as your study group, you could form a project group and log all your ablations to your project group. And then there's like some cool things you can do regarding filtering. You'll be logging your, if you are really organized about this, you could like log things based on your model, your learning rate scheduler, and that'll give you a really easy way to like filter through your different ablations to more effectively find things that work and make decisions regarding it, right? So you might have done things like this. Oh, one very important thing is checkpointing your model. Some of you might not be using runtimes that are not persistent. So like the moment you disconnect, your data is all gone. So try creating checkpoints. If you have a well-performing model, do save it. We sometimes randomly pick a model. Like while we're testing your homeworks, we'll pick a model and run it. And if you don't have a model, that could be an issue. And and 1DB, I think 1DB provides you with a certain amount of storage to store your models. And there's also facilities regarding resuming your training. And you can look at the 1DB recitation that we have for more information surrounding this. So another thing which could be useful while you are like, there's two ways to go about this. You could either start this to find your baseline, but ideally have just one member in your group do it. Or you could do this at the end, while like let's say at the end you have a decent performing model and you want to squeeze some extra juice out of it. So you do something called a hyperparameter sweep, right? So 1DB can automate to some extent the process of cycling through these different hyperparameter configurations. And then like it'll be logging all the metrics, and hopefully you can make some decisions regarding it. You could do it at the beginning, but your search space is huge. This does take a lot of time to run. Ideally, you would be running it parallelly, but you would need multiple sources of compute, which you most likely don't have. So things will be sequential, and that will take a long time. So the way we did it during our groups was to find a good model that process ideally the high cutoff. And if you have more time, run a sweep at the end where when our search space is greatly reduced, right? We found like a subset of things that work really well. And we just want to sweep on those things to see what works. Because like I said, these things can take time. We do have a recitation covering this, but it is very easy to set up. You decide on a stopping criteria, like which could be like the number of epochs or a certain metric. You decide on the kind of search you want to do. You could do a grid search or a random search, and you decide on what parameters you want to do your searches on, like what different combinations of parameter, and 1DB should take care of the rest. Watch the video for more information. But yeah, there's some caveats. It can be really time consuming. Certain search strategies don't really work that well. Like a grid search, you'll just be searching for things in a grid. But random search, if you're not picking the right thing randomly, might be wasting time. So like I said, the best way to address things like this would be to like limit your search space. So kind of run the sweep at the end. And what else? So yeah, in general, you could do it at the beginning to find your baseline, or and then everybody runs an ablation based on that baseline, or you could do it at the end to squeeze some extra juice out, or you could do both. It really depends on the amount of time you have. All right, so we'll get to some homework 1, part 2 specific tips. You guys might have been seeing a lot of these issues pop up on Piazza. So, but the this is a weird thing about deep learning is there's really no set answers at times. So just try different things out, provided you have the time, right? Read papers, read different blog posts, um, go beyond what's in the write-up if you can. Remember to shuffle your training data set. We see a lot of this. Don't shuffle your test or validation set. Choose your learning rate wisely. This should probably be one of the first ablations you run once you find your baseline. Like, what are some acceptable learning rate values? Your initial learning rate values. So, like, pick the most basic scheduler and just find the initial learning rate values. There'll be some values where the training will be really slow, and some values where you might just get like your weights might just blow up. Choose batch sizes. Smaller batch sizes, you could get some sort of a regularization effect, but you might have more variance. So yeah, try things out. All things to add to your experiment matrix. Oh, ensembling. I've never done this. I don't know if any of the TAs have ever done this. I definitely wanted to try it. There's this, I think you guys learned about cosine annealing with warm restarts, where you guys just keep dipping the learning rate and then going back up, keep dipping the learning rate. So there's a really cool paper about this where while you're doing the cosine annealing with warm restarts, you with every restart you get these like little models which perform very well, and you could ensemble all of them and get your prediction as a majority vote between all the between all the models, right? So I haven't tried this. So if you try this and it doesn't work, don't call me out. But hey, if you have the time, definitely give it a shot. All right, so guess this should be inference mode while evaluating. Don't forget your zero grad. Experiment on learning rate schedulers. Something to add to your. So here's there will be you guys will have to pick and choose while running your ablations, right? Like it is very possible that there's something else that just works better, but there's a time limit here, right? So if you find something that's working somewhat reasonably, just stick to that and try experimenting with somebody else. But yeah, you guys will have to make that judgment, and the more you do these assignments, you will get better at making those judgments. All right. Pretty self. You can just read this on your end. Oh, this is important. So you might get CUDA errors. Those error messages are not really informative. So something you could do is just switch everything back to CPU to get error messages that are more readable. There's also other messages. There's also other ways to do this. You could attach hooks to CUDA, but I recommend this. This is much more easier. This is something that was brought up on Piazza, and yeah. So essentially, batch norms. A batch norm might not be. It's pretty much. It might be redundant to have bias equal to true while using batch norm, and so setting bias equal to false might just save you a few parameters while potentially giving you better performance. But these are things you should like just read articles, just read blog posts, read papers, and there'll be more little tidbits like this which you could figure out on your own. There you go. All right. Well, that's pretty much it. Thank you guys for listening. I think we'll be moving to the second part of the evening, which is bootcamp, hackathon, something. Cool. Thank you. Sorry, what's it?
So for our application studies, we are sharing the hyperparameters, we're sharing every single detail of the model. But for our final submission, we still need to train our own individual model.
Yeah.
Not the same parameters, exactly everything.
Can you use the same parameters? Like, let's say as a group, you guys figure out a model that works best. Can you use the same parameter?
Yeah, you can use the same parameters, but again, your model will be your own. So you will be submitting everything as an individual. So, and at the end, we'll be randomly checking, your model and, just grabbing that file and running it against what you have submitted. So even though the parameters could be the same, but, everything else, would be your own, like the coding wise.
Yeah. I think you can't share code. You can share high level details, but you can't share code. So let's say you're using Convex for homework part 2, and you tell your teammate Convex works really well. You can actually share the code of how to implement Convex. They'll have to do it themselves. Any other questions? Sorry, hey.
Yeah, I mean, it stands to reason that like we have a similar architecture and we're using the same hyperparameters. Can you go over again what we're supposed to do in our homework? Like, do we just disclose who we worked with at the top when we submit? Because I don't want to be confused for like us having a bunch of similar
No,
code.
so you don't do that. Your project groups will be formed, your study groups will be formed. You'll be sending out the list soon.
Okay.
When you are about to submit the files, you will, mention all of the details, like all of the tests that you have performed. That could be the same for the group, but that should be a decent enough subset, for us to know that okay, this group has done its submissions and this group has done its, rigorous testing.
And also, we'll ask you to perform your submit your logs in the future. So we'll get a pretty good idea of that. But we're pretty flexible when it comes to collaboration here, as long as you guys don't like share code or whatever. Like even like the purpose of these boot camps is for you guys to share your ideas about the things that worked, that didn't work, and you guys aren't necessarily restricted to your study group. So please do share things that work.
At the end of the day, it's a team effort, but that, but with reasonable limits. Like it doesn't have to happen like, okay, one person on the team is doing everything, all the testing, and the other members of the team are just, copying what he's doing. So that should not happen. You should like sensibly divide the work, divide the hyperparameters testing among the team. And that's where, your ablation sheet will also come into play. Like, every team member will log what they have tested, and we'll be checking, when you submit that.
Yeah. Do you have any more questions? Sorry, what's happening? Sorry, what? Yeah, you can, but are you a student? You shouldn't be asking this, man. Take the course again next semester. All right.
Just to reiterate the fact, the total number of parameters, I know this has been a lot of confusion on Piazza. The total number of parameter limit is 20 million. Just to say it again, it's 20 million.
20 million. Oh.
No, not 24. There was, I think you missed on the slide.
Oh, slides. Oh, my bad. It's
Again,
20
saying
million.
The parameter limit is 20 million.
Also, if you guys do ensembling, we count the parameters of each ensemble. So if you are doing a 4 model ensemble and each model has 20 million, that's 80 million parameters, and might get a 0. Sorry, what's up? What is 20.5 million?
20.5? Yes, that will not be counted.
It's 20.5 is not acceptable. All right. And any more questions? Is that it? All right. All right. Thank you, guys. Thank you for listening.
Are you connected?
No. I just wanted to ask them, have they formed their groups?
Okay.
Guys, have you formed your groups? I hope all of you have formed the project and the study groups. Anyone remaining?